I'm very happy now to introduce my colleague, Dr. Bob Brecha, who is serving currently as the research director.
Sound a little bit. I don't know if you can
Pardon me?
adjust that.
He's losing sound.
There has been a little bit of wobbliness in the audio. We could understand everything you said, but it's been a little staticky. So, are you hearing enough to understand?
Oh, it's unfortunate. Well, okay.
Well, let's hope it comes back together. But let us know if you need us to. Can you hear anything right now?
Yes, I can.
Okay.
It's good.
Okay, good. Let's hope it went in and out here, so let's hope it's more in than out as we move ahead.
Okay, I'm sorry about that.
That's quite all right. Thanks for letting us know. I'm happy to introduce my colleague, Dr. Bob Brecha, who's serving as the research director for the Hanley Sustainability Institute and has, for much longer than that, been a professor of physics here at the University of Dayton. He received his doctoral degree in physics from the University of Texas at Austin. He teaches in the Renewable and Clean Energy Graduate Program and coordinates the Sustainability, Energy, and Environment minor and other initiatives sponsored by that same program. Since 2006, he's been working periodically as a visiting scientist at the Potsdam Institute for Climate Impact Research in Germany. His most recent research includes energy and environmental issues, and a particular interest lies in tying together climate, economic, and energy system models and thinking about the consequences of coming fossil fuel depletion challenges. I invite you to join me in welcoming him to the podium.
Thank you, Una, and Vince for thinking about how to put together the science and the spirituality, or as I was thinking about while Dr. Christie was speaking, we're now moving sort of from the sublime to the scientific, or from the spiritual to the secular, and that's good. I think that's a really good thing. As Otmar pointed out, this conversation is important, and it's something that I've been happy to be involved with for many years here at the University of Dayton. Probably 15 years ago, I was part of a seminar for faculty on religion and science, where we hashed out some of these issues in a very interesting collegial discussion over a whole semester. So this is continuing in that vein. The other thing I would like to say, at least my point of view, is that Laudato Si is really a deep statement of the idea of strong sustainability, as it would be called in a more secular context. It's the idea that nature sets boundaries for us, that our social systems and our economic systems have to operate within the boundaries set by the physical world. In the case of climate change, it's the space in the atmosphere to absorb CO2 that sets a final limit in that sense. So really there's a way that I think that this Encyclical has made an impact well beyond the world of Catholic theology and of Catholic social teaching, in that it was anticipated in completely secular professional scientific conferences for the better part of a year, where it was remarkable to me to go to the American Geophysical Union conference of up to 25,000 scientists and hear the coming Pope's encyclical be mentioned at this conference as a potentially important turning point in the idea of how we deal with climate change. And that was just one example. I heard it at many different conferences. So this has been very interesting to hear and to see. The other thing I would say is I don't have a PowerPoint, and I'm a scientist, and so this is kind of unusual. And I'm doing that intentionally. And I'm doing it intentionally because one of the things I've learned over time, giving a lot of talks on climate change, is that data don't matter at this point. And that's not to say science isn't important. That's not to say that the data themselves aren't important and that we shouldn't be doing the research. But that's not the way that we convince people to change their minds or to act on climate change. At this point, we know the science. It's been known for a long time. And we actually know the technologies that we need. Every technology we really need to address climate change is available already. Now, there are questions about cost, there are questions about social acceptance and things like that, but we could do this. And so we know the problem and we know the solutions, and therefore my sense is that presenting more graphs is not going to help that much. Now, this doesn't mean that since my job here is to talk about the science of climate change, it doesn't mean I'm not going to talk about it. I am going to talk about it, and so I'm just going to give a really brief overview of some things, and maybe with the, since I don't have the aid of my graphs, I'm going to sort of give a bigger picture of how I think about some of the climate change science arguments. I'm not going to try to delve into the theology. That's not my job here. The first point is, in spite of the fact that I just said this, there is no such thing as climate science, in my point of view. There's just science. There's chemistry, and there's physics, and there's biology, and there's geology, mathematics to help us out as a tool. There's no climate science. It's just application of the science we know and that we've been using in many other areas for decades and for centuries. Now, I'm also not somebody who says, okay, it's only science and we just need to follow the scientists, but the idea that there's a special climate science somehow gets in the way of the discussion, I think, sometimes, that says there's something special that's been invented probably by this giant conspiracy of people around the world for the last century that's trying to convince us to destroy our economies. There is no such thing as climate science. There's just people who do physics and they do a chemistry, and if they're like me, they've been trained in physics, and they realize that there are strong applications of our scientific knowledge to the climate system. But it's not climate science. I've given a talk in the past called From Cell Phones to Global Warming, where basically the argument, I'm not going to go through it here, is basically, look, if you believe your cell phone works, then you should believe climate change and global warming, because the science is no different. It's there. And in fact, there's some pretty direct relationships between how we know things about the climate and how our cell phones work. The other thing I'll make the point of is that this is not even new science. The science of understanding the climate is absolutely not new science. Fourier in the early 1800s was one of the first ones who said, there's a layer of the atmosphere that's probably helping keep the planet warm. And in the 1850s, John Tyndall did experiments in the lab that said, if we shine infrared radiation, infrared light, heat, through certain gases, wow, it gets absorbed. And other gases, like nitrogen or oxygen, it don't absorb this infrared radiation. Carbon dioxide does. Well, that was in the lab, but the direct relationship and why he was working on this was partially to understand Fourier's statement, there are gases keeping the Earth warm. Which gases are they? Oh, it's things like water vapor and CO2. So that's a lab experiment 150 years ago that was showing the principle of what we're talking about now. And in the 1890s, a chemist, Svante Arrhenius, made the first climate model. He was trying to understand the glacial and interglacial cycles. It was very early attempts to understand this, but he was using what we now call energy balance. Basically, the energy in from the sun has to be balanced by energy, radiation going back out to space. That's a really simple principle. If you have more energy coming into a system, whether it's a pot of water or the Earth, than you have going out, then it's going to heat up. Or vice versa. If you have less coming in than going out, it's going to cool down. Arrhenius was trying to figure out some of this stuff in the context of the Earth, with knowing that CO2 was an important gas. He was making pretty sophisticated measurements. Above all, I'm amazed at the fact that he made climate models, pen and paper, or pencil and paper, that were actually spatially resolved. That is, he came up with answers for if we were to double CO2, how much would the temperature of the Earth rise? And oh, by the way, would it rise more at the poles than it would at the equator? And he said yes. These are things that we now know. These are fundamental pieces of climate models now, is that doubling CO2 leads to a certain temperature change. His answer was a little bit higher than what we say now, but not much. He also said if we cut CO2 in half, what would happen? He also happened to say two other things. One of them was we would never be able to double the CO2 in the atmosphere, so this is just an academic exercise to calculate what would happen. Well, we're well on our way to, well, I hope we're not on our way to doing it, but we could. If we burn even a small fraction of what Otmar was talking about is in the ground. The other thing he said was, hey, this might be kind of a good thing. He was from Sweden. He said this, and we still hear that statement too. So in the sense of the basic physics of the climate, that's 120 years old now that he published this paper. We're still using this, we're getting the same results now. So this isn't new science, and I think that's really important to keep in mind. Unless you want to say that our conspiracy theory now involves not only scientists all over the world of all ideological stripes, and it's been going on for 120 years and we haven't noticed it, and nobody's come behind it yet. So anyway, it's not new science, and it's just science as usual. So past climate change, I mean, the evidence we have are things like oceans, little shell creatures that get buried over time. We understand, you know, scientists have gotten really clever in the last few decades of understanding how to use proxy measurements. How do you go into buried stuff in nature, dig it out, and understand what's inside shells? How do you go into the ice in Antarctica and dig out a core and understand as you go further down into the core that you are going back in time? There's a well-known book by Richard Alley called The 2-Mile Time Machine, where you dig down into Antarctica a mile or two, and you are really going back in time and seeing what the Earth looked like over that time period. You dig out a core, you slice it up, you look in the slices, there are air bubbles. Those air bubbles have carbon dioxide and other gases, and you start out of each slice back in time, you look and see what's the percentage of CO2, and you map that out. So as we've gone further and further along this line of trying to understand more deeply the climate system, scientists have gotten clever in the way they make their measurements and the way they try to go back further in time. One of the most interesting ones I found over the last several years was a paper that was published in, I think it was in Nature or maybe it was in Science, one of the top science journals, that you could call a snake thermometer. Essentially, animals grow to certain sizes partially depending on the climatic conditions around them. And so this was a measurement that essentially looked back at some South American boid species snakes and saw that they were growing to enormous sizes 20 million years ago, and using that, sort of that change over time as a kind of thermometer. How big were the biggest species over time, and does that tell us something about the temperatures that were existing at that time? Now, I think it's not clear that this was the best thermometer that we have available, but it was an interesting thought experiment to try to look at this kind of a system. Just get more and more measurements. And the questions, the answers are always the same. Yes, Earth's system has changed over time. We know that. We understand a fair amount of why it's changed over time, and we understand now, at least since Arrhenius, that adding CO2 to the atmosphere in large quantities will cause a big change in the Earth system. And these rhythms of natural changes are very evident in, for example, the ice core measurements, where you see the famous graphs that almost everybody, I assume, has seen, where there's over the ice ages, the CO2 levels go up and the temperature levels go up, and we understand how they're synced together, and we understand the causality of those changes as well. We understand the natural rhythms. There is natural climate change, and then there's climate change that we can induce as a human species, and it's one of the most worrisome things for scientists, and I would then say by implication should be one of the most worrisome things for all of us, is the rapidity with which current climate change is occurring. It's partially the magnitude, but it's how fast it's happening. We can see the sort of slow natural rhythm of the Earth, even going from an ice age to an interglacial period, as has happened here 10 to 12,000 years ago, where this area would have been under roughly a kilometer of ice during the deep depths of the ice age. Now we're not. Something changed, and it changed fast on a geological scale, but the changes we're seeing now in both temperature and in CO2 concentrations, but especially temperature for this particular argument, are at least 10 times faster than those glacial to interglacial period changes. So it's not just the signal itself that's a measure of what's happening, it's how fast. And so all that stuff feeds into our understanding of what's going on, and really I mean that, understanding of what's going on. It's not, my cousin of mine who is somewhat of a climate denier once said, yeah, but it's just all statistics, and with statistics you can prove anything. Well, it's not statistics. It goes back to the science. We understand physics and chemistry and biology and geology, and that's what we use. It's not just a statistical correlation. It's causation that we can add to that conversation. So that's the past. What about current climate change? I can get personal with a paper that I worked on with some colleagues in the biology department, where a local resident had been making observations for almost 30 years in her own garden of the first flowering times of various species. She would walk around her garden every day and record in a diary. When did she first see this species? When did she first see this species? My colleague Don Geiger, brother Don Geiger, made me aware of this. We talked about it. We talked to her. She gave us the data. And we had a student start sorting through 27 years worth of data entries of handwritten. This was not a climate scientist. This was just somebody recording information. And we didn't tell the student at the time. My initial hypothesis was that she wouldn't find anything, that the data wouldn't show any signals. But they did. And we were able to then correlate the temperature changes over that same time with the first flowering times of different species, show how much the advance of spring was essentially due to changing temperatures. And this fits into a very broad body of literature. There's a huge literature by now of exactly these kind of measurements. For example, going back to Thoreau's diaries at Walden Pond, where he made these kind of observations of different species and the flowering, the budding times of trees. These are still data that are being used and being mined to get information about changing climate. So we see these things. They're around here. More generally, though, there are lots of indicators. There's a focus, and I sometimes get a little bit defensive about some of the political debates, and it has to do with the temperature and the temperature of the satellites or the temperature of the surface and whether they're showing a change or not. This is just a nonsensical discussion, for one thing, because the temperatures are rising. So, I mean, I don't know what the argument is, except that in every measure we have, the temperatures are rising. But beyond that, there's a whole slew of data for all kinds of different things. We've got the Arctic sea ice melt. We have the decreasing pH of the oceans. We have sea level rise. We have heat content in the oceans. We have the ice sheets melting. There's just so many different pieces of evidence that all go in the same direction. And so the idea, and I realize I'm probably preaching to a choir that's already been converted, but the idea that we are hanging on this thread of one particular temperature data set or another is beyond ridiculous. We have really a whole set of things, and there is simply no other remotely scientific explanation that can describe all of these phenomena at the same time. You can imagine solar activity being partially responsible for some of the temperature rise. Well, okay, that might work. It turns out it's only at best 10% of the explanation. But then what about the acidification of the ocean? That can't fit in there. And so there's only one explanation we know of that gets it all in one package. And that's important. That's what we as scientists like to see, that we've kind of got all bases covered. We don't know everything. There's lots of things to still investigate, but the basics are there. And what about future climate change? So I've gone to the past, I've gone to the present. The future climate change, well, this one's simple in principle, difficult in practice. It just depends on us. I mean, that's what Altmar was saying, right? That's what the future holds, is what we decide to do. Because we know it's CO2 that's the main culprit. There's other things too. We know now, to a fairly good degree, if we set a temperature goal, what's the amount of CO2 that can be emitted, the carbon budget that he keeps talking about. It's our choice. That's all it comes down to. I mean, we can make projections of how good or bad it could be or what the changes could be, and there's uncertainties there. The impacts are somewhat uncertain, but we have very robust projections for many impacts. For example, sea levels will rise, and sea levels will keep rising for centuries. We know that's going to happen. So map out what that means if you live in Miami, and you're already seeing impacts. What's it going to mean if the sea level rises by a meter by the end of the century? All right, we know what the impacts are at a high enough level to know that we probably should act, and that we're going to have consequences if we don't. We know about desertification in certain areas. We know about acidification of the ocean. We know what these impacts are. So the future is really ours to decide. And let me just finish by saying that takes me back to some of the things that Otmar talked about with the carbon budget, but it takes me back all the way back to the beginning of my talk where I said the graphs don't matter, because all this stuff has been published in multiple IPCC reports and thousands of scientific papers. It's not the science that's really in question, certainly not in the scientific community. It's how do we make people, how do we encourage people to act on that science? That is the big question. And so that's why I'm glad for the rest of this weekend I'll be able to hear how theologians and others talk about that, because that's really going to be the big challenge. We've got the technology, we've got the scientific background, we can do all that. How do we make people appreciate what has to be done? Thank you.